Hello, everybody. I'm just going to give it a minute or so to let everybody get into the webinar. All right. So once I see numbers have leveled off, I'll make a start. Okay, right. Well, thank you very much for attending the Super Solar Floating Solar Workshop. We've got a packed program of speakers for you this afternoon, whose names are there in no particular order. On the exciting subject of floating solar, which I expect is going to be appearing in the news more and more as the solar installations are going to be ramped up across the globe. So obviously this subject has got some great challenges, and we're going to be hearing about those and the solutions to them from our speakers. Now, first of all, I just want to spend a minute or two telling you about Super Solar, who have organised this webinar in conjunction with our partner organisation at the SuperGen Offshore Renewables Energy Hub. Super Solar is an inclusive community linking solar research and industry in the UK. Started in 2012, and one of the things we try and do is provide regular opportunities for early career researchers in the field of solar PV materials research to present their work and make connections. And one of those things that we do is put on topic focused webinars like this, and we do many of those over the years. And a lot of them are still available on our website. So if you see the website link there, Super Solar Hub, you can go and look at the recordings of previous webinars that we've had in topics, for example, the circular economy of PV materials. That was our last one. We're on Twitter, we're on LinkedIn, we've got the website there. And if you go to the website and join as a member, you get, of which 750 people have already done so, you get a regular newsletter with updates about things that are happening in the PV world and events and opportunities that might come along. We also in the past have provided funding for young researchers to take international industrial secondments and for to attend international conferences. And we put on free places for major events. So, for example, there's the big perovskite meeting taking place in Oxford next week, PSCO, and we've sponsored free places to a number of students to attend that. And we have some great speakers today. There's the full list and all their titles of the talks that they're going to be giving later on. And if you want to ask them a question after their talk, we'll be having a little Q&A session for each of the speakers. Please put your questions written down into the Q&A function rather than the chat. So please do that as they're speaking, and then we'll get to the questions at the end of the talk. And there we are, there they are, and that's all from me. And so I'll invite our first speaker, Pratik Joshi from NREL in the USA. So Pratik, if you'd like to share your screen. There we are.
You see that okay?
Yeah, I can see that fine. It's in presentation mode. So please go ahead, Pratik.
Great, thanks everyone. And yeah, hello everyone. My name is Pratik Joshi. I'm a research engineer at the National Renewable Energy Laboratory, also known as NREL. And one of my roles there is supporting the lab's research portfolio on floating solar photovoltaics, or FPV. So to kick off this webinar, I'll just be giving an overview of some of NREL's research on this topic. Also, we'll be highlighting some of the technical potential assessments and my hope for this is to provide some helpful context and background information that I think will be very helpful for the following presentations that you're going to listen to, which may be deeper dives on some of the topics that I'm introducing. So just a quick introduction to NREL. For those who aren't familiar with us, we're based in the United States. We're a Department of Energy national laboratory, and we focus on research and deployment for renewable energy, sustainable transportation, energy efficiency, and systems integration. We partner with industry, academia, other government agencies, work on many international projects as well. So today I just want to start with an overview of FPV, then talk about some of the research activities happening, not just at NREL, but across the world, and we'll hear more about that later today as well. And then I want to conclude by just spotlighting the technical potential assessments and focus on one that we completed recently. I usually like to introduce the topic of FPV by first thinking about where solar PV technology in general fits within this broader energy, water, food nexus. And that's a topic that covers how these three critically important industries interact with one another. For instance, if we look at energy and food, we can see that there's often competing land use for food and energy production. And of course, food production requires energy. So if you're familiar with agrivoltaics or agri-PV, that's where this would fit in terms of solar PV technology. For water and food, well, food production could impact water quality and availability with fertilizers, water shortages, contamination could also limit food production. We hear a lot about aquaculture in this space. And then moving on to what we're focusing on today, FPV, that can be found at the intersection of this energy and water nexus. Of course, water shortages could limit energy production, and then water infrastructure requires energy. And then at the intersection of all three, I've put aqua PV or aquaculture and solar PV. That's not the focus of today, but just helps you figure out the landscape of things. So just providing a quick overview of FPV systems. This is a schematic of a typical system, and I just want to go over the important components. Well, the modules themselves, the solar panels, are typically the same as those used in ground mount or rooftop installations historically. I've seen increasing interest in academic papers and deployment on tracking or bifacial technology. Those are commonly used now in the land-based industry. Historically, floating solar panels have been sited on artificial water bodies in freshwater, think reservoirs, retention ponds. Now we're seeing more deployment on natural water bodies and then also offshore. And you'll hear more about the offshore applications later today. Of course, the whole host of different considerations. The floating platforms that exist today consist primarily of HDPE plastic. Of course, there can be different considerations for offshore sites, both in terms of the material and the structure. And then on this schematic, you see anchors, bank anchors, and mooring lines as well to minimize the movement of the system. Then we have our electrical components as well, generally similar to land-based systems. This schematic is just showing you the central inverter located onshore, but then we have our cables connecting the modules to each other and then connecting the modules to the inverter. Those might need to be rated for freshwater or marine environments. This chart showing the market growth is from Wood Mackenzie. It's a forecast of annual FPV installations out to 2031. So you can see there's projected to be a sustained high demand for annual installations. This is in terms of a megawatt capacity. Most of that is concentrated in the Asia Pacific region. People are often interested in how the cost of an FPV system could compare to a similar land-based system. So a couple of years ago, some of my colleagues conducted this economic analysis, but of course, this was a couple of years ago. Some things may have slightly changed since then. But they basically have had a lot of experience modeling the cost of a ground mount system broken out into the different subcomponents. And then they looked at a similar FPV system in comparison and saw that the installed cost, just that upfront cost, was about 25% higher per watt. And that was largely attributed to these structural components that I mentioned a couple slides earlier. So the cost of the floating platform, the anchors, the mooring lines, and that's obviously, of course, very site specific as well. Then they also looked at this common metric that many of us are familiar with, levelized cost of electricity. And that was estimated to be about 20% higher for FPV in this particular, with these particular assumptions. This accounts for the higher upfront cost, but it also accounts for higher energy production from FPV due to greater efficiencies, and I'll touch on that more in a couple slides. And also a lower operating and maintenance cost assumption. I just want to note that this cost analysis doesn't account for some of the other co-benefits like land use benefits and things that are harder to quantify in some of these metrics, but that's a nice transition to my next section on research activities that also related to some of the co-benefits of floating solar. Again, a few years ago, some of my colleagues conducted a systematic literature review of the potential co-benefits of FPV. They looked at social, economic, energy, water, food, and land benefits. And then for each of them, they tagged it as empirically confirmed, theoretically confirmed, or unconfirmed. So some of this may have also changed in the last 2 years with more research that's been done. And this is the full list. I don't have time to dive right now into all of these, of course, but happy to share these resources after as well. I just want to highlight a few for today. So under social and food and land benefits, this is where we have the reduced land use if we're taking advantage of a water body and that land can be repurposed for other things. Under economic benefits, we have the increased ease of installation. We don't need to prepare the site. There's less site preparation costs. And then the energy benefits, one that often comes up is this increased panel efficiency. And that's because solar panels are typically more efficient at a lower operating temperature. And that air temperature above a water body is usually lower than the air temperature above land or rooftops for a variety of reasons. So if you have solar panels sited on water bodies, they're generally operating at lower temperatures and thus more efficient at converting that sunlight into electricity. So this is a nice snapshot of how we view the research space for floating solar. To date, our activities at NREL have mostly been focused on this analysis and implementation bucket, whereas we're going to hear more about some of the technology research as well and monitoring real-world systems. I'm going to dive a little bit deeper into this topic about policy and regulatory issues, about the costs and benefits of co-locating floating solar with hydropower, and also looking at the investment opportunities and technical potential. This report here focuses on some of the barriers to floating solar in Southeast Asia specifically, but many of its takeaways I think are relevant to other regions. The authors looked at barriers that were cultural, environmental, economic, regulatory, and related to hybrid systems. For hybrid systems, we're talking about floating solar that is co-located and also jointly operated with existing hydropower. I'll just touch on the regulatory component. So they looked at different barriers. Well, there could be uncertainty about water rights. Who owns the water body? Who can develop on it? That could delay project development and increase permitting costs. Also, water bodies are often not regulated by the same agencies that oversee energy infrastructure, so a lack of interagency cooperation can be a barrier. Then finally, any lengthy, expensive, or most importantly, I think unclear environmental approval process can make these projects more difficult. So to address these regulatory barriers, best practices could include developing clear policies around water rights for FPV projects. Also, if you have multiple agencies involved, having clear guidance for interagency cooperation, as well as environmental approval, can help remove some of these hurdles. So, we feel it's very important to ensure that the environmental impacts are mitigated, and also that the process for doing so is clear to developers. So I think later today as well, we'll have a presentation on environmental impacts of floating solar and some of the research there. We also examined the research question of, well, what are these operational benefits of co-locating and co-operating floating solar with existing hydropower dams? So to do this, we used some of our openly available modeling tools. We first modeled the configuration of a hydropower only system where you have hydropower feeding into the transmission system and then another node connecting coal and gas. We then modeled a standalone floating solar system. So this is the same as the hydropower only system, except we add floating PV into the mix, but that's connected at a separate node. And then finally, we compared all these results to that of a full hybrid system. So you could see floating PV and hydropower connect to the same transmission node. This simulates a system that is co-located and jointly operated with the hydropower plant. And then looking at the results across the scenarios, we had a couple key findings, one of which is that compared to a standalone system, this hybrid system could help conserve water resources by shifting hydropower generation to other periods of the year, because of course, hydropower is dependent on seasonal rainfall. Itself is not unlimited throughout all times of the year. So this dark blue line is showing you the hydropower only scenario. The lightest blue line here is the full hybrid scenario. So you could see during these months, and I believe this was for a Southeast Asia country, from about June to September, you have lower hydropower output. It ramps down, and then that is used in other times of the year as well. We also found that the hybrid system helps lower curtailment of solar, particularly when transmission is congested. The light yellow line here shows you the production of solar in a standalone system, and that's lower than the full hybrid system during most of the year. That full hybrid system is the dark gold line, and that's due to the curtailment of solar. So the transmission system is too congested, solar has to turn down, but when you jointly operate solar and hydropower, when instead of curtailing solar, you can reduce your hydropower generation, helps reduce solar curtailment. That hydro is used in other times of the year. So overall, you're relying more on solar and hydro than you would in the non-hybrid scenario, and that can have a variety of system benefits. So very rapid fire, just summary of some of the results there, but I also want to shift our focus now to cover some of the technical potential assessments. That's something that we've done a lot at NREL as well. And we recently completed one earlier this year for Southeast Asia. First, I just want to share a snapshot of some of the technical potential assessments that have already been conducted at NREL and by researchers across the world. So here are two global assessments that you can reference later as well, looking at what is the role that FPV can play just globally with a variety of data sets. There have also been a variety of national and regional assessments covered. So one covering the US, Brazil, European Union, continental Africa. This is the one in Southeast Asia that we've recently done. So this may not be comprehensive of all that's out there, but just a quick search that I did. And then we also have conducted some subnational assessments. So zooming in even further, this is for the US state of Colorado, where NREL is headquartered. And this study not only looked at the state of Colorado, but it also picked a couple specific water bodies, and it's looked at the potential for FPV on those by considering site-specific characteristics like evaporation impacts, algae growth, wildlife impacts, water quality, land use trade-offs. And there's important differences here in terms of the water bodies that they assessed. Some looked at only hydropower reservoirs, some looked at all reservoirs, some included lakes. There's different assumptions about the technology and also different data sources, maybe for the water bodies or for solar resource. But I think all of them in their different regions can provide important context on the role that floating solar can play. They can inform policymaking, target setting, and planning for power systems. So for the recent Southeast Asia study, we looked at both reservoirs, hydropower and non-hydropower and then natural water bodies such as inland lakes and ponds, and we have our different data sets here. We also collected data on infrastructure to inform where floating solar could reasonably be developed. So we collected data on transmission lines, major roads, protected environmental areas. And then finally, we utilized our high-resolution solar resource data for Southeast Asia that was created for a separate project and that we leveraged for this one. So as I mentioned, for water body types, we looked at reservoirs and inland water bodies. These are so natural water bodies that were not artificially created. And then we looked at monofacial, bifacial panels that were fixed tilt. We did not look at offshore areas. We also did not look at one-axis tracking. So I think these are two important areas for future examination just in general. Now we're going to be hearing about offshore more later today. So we started our calculation by first excluding all water bodies that were in protected areas or as a proxy more than 50 kilometers from the nearest major roads as a proxy for developable sites. We then had different sensitivities. We varied the minimum and maximum distance from shore to provide a range of technical potential for floating solar. This information together gives us our suitable area in kilometers squared, suitable area that could be developed for floating solar. Then we have our technology assumptions such as power density, how many watts per square meter, for example, are we assuming? That can give us our technical potential for capacity in gigawatts or megawatts. And then we use our solar resource data that I referenced earlier to model the energy generation of that floating solar. So we run it through some of our open source modeling tools to get our generation values. And so technical potential can be thought of more of an upper bound estimate. It doesn't look at economic potential, which could be a subset of that, and then what you can actually develop. This is a snapshot of some of our results. Again, we had a couple different scenarios. So this is for reservoirs, and we have the water bodies, the range in area, capacity, and generation. Those ranges are due to different assumptions for the distance from shore. And then we also looked at natural water bodies. So these are the results there. The potential for natural water bodies, just based on the number of water bodies in that data set, was much greater. But of course, there could be significantly higher limitations to developing on a natural water body due to environmental constraints or concerns. But also our stakeholders were interested in looking at this, so we wanted to also help quantify that as well. And then last but not least, we integrated all this data into the Renewable Energy Data Explorer platform for anyone that's interested. So in addition to the report and the slides, this raw data is also available. So we have this technical potential tool online that can be used for wind and solar, but now we added a technology type for floating PV. So for the countries that we covered in Southeast Asia, this floating PV data is now available. So you can set some of your own inputs. There's some presets here, but you can change what the assumptions are for minimum or maximum distance from shore, distance from roads, transmission lines. And then you can change the water body type as well. And then that gives us the results in table, chart, map format, and then also available to download as a spreadsheet file. So that's basically all I wanted to cover today. I think I'm at my 20 minutes or so. So I'm happy to answer any questions. If there were some in the chat, I'll take a look. I couldn't see them while I was presenting. But yeah, thanks. I'm happy to kick this webinar off and looking forward to any questions. I will have to drop shortly and I'll rejoin the meeting as well to answer more questions. But yeah, thanks everyone.
That's great. Many thanks, Pratik. Now, if anybody has got a question there, I'll just reiterate, just type it into the Q&A and we'll put it to the panelists. And if any of the panelists want to raise their hands and then feed a question in, then we can do that there. But just to start the ball rolling there, Pratik, a lot of your work is theoretical there. Do you, NREL, have any plans to make any sort of test floating PV test bed anywhere?
Yeah, That's a great question. We do have some early stage plans. It's in the works to, have a test facility as well, to try to, monitor some of these systems in real time. For instance, I think a nice helpful analogy is with our work in agrivoltaics or agriculture and solar PV, and there's been a lot of work done there across the world in NREL, and we recently, on a plot of land on campus, have installed solar panels, planted crops underneath there, and have been using that as a test bed. So, I'd love to have an floating solar test bed as well. So that'd be great. And I know some research universities and other places have that. So it's great to learn from those insights.
Hopefully soon. So I've got some questions in the Q&A there. So one from Lana Nyberg, who says, why are FPV potential in APC higher than the USA? So Pacific coast. Yeah,
sure. I think so. I'm not sure if you were referring to the slide on that was showing the market growth, but if that was the slide, that wasn't necessarily referring to potential, but like projections for the market going forward. So for that slide, a lot of the floating solar has already occurred in the Asia Pacific or is projected to occur in Asia Pacific for maybe a variety of reasons, land use constraints. In the US, we have just a lot more land available, and that's also used for agriculture and other purposes. But in terms of technical potential, I don't think I haven't looked at a comparison of the US and Asia Pacific, but there's a lot more available land, I think. So maybe floating solar is not as common.
I think Mike Walls has got a question there. So if you want to,
Pratik, thanks for a great talk, great overview of floating solar. I was just wondering about the issue of public acceptance, because in a much smaller country like the UK, these water resources are used for leisure activities such as sailing, fishing, etc. How do you think the public would react to these water facilities being covered in solar panels?
Yeah, that's a great question. I do think like any energy infrastructure, like onshore wind, there is you could run into public resistance, and we see that in the US East Coast with offshore wind even, and people having issues with it in terms of the aesthetics. So the report that the NREL researchers did looking at some of the barriers covered like cultural barriers as well, just in terms of public resistance. And I think the recommendation was not super unique to floating solar, but in terms of sharing what the benefits are, like what are the benefits of floating solar? Well, it would reduce the amount of land that would need to be used for this critically important energy infrastructure. And it doesn't require covering the entire surface area of the water body with panels as well. And so I think if people are aware that, well, this is using a water body and not taking up land space, they might be more amenable to that. And then, maybe not covering an entire water body. That's if it's used for leisure recreation.
Okay, we've
maybe no simple fix.
An interesting question about the effect of FPV on shipping radar system. Are you aware of any potential effects?
I am not aware of that. Yeah,
I think we can dismiss that one.
Yeah. Sure.
And I'll just take one more before we move on. And just somebody's asking why is Southeast Asia selected for this example. Perhaps you explained that earlier on, didn't you?
Yeah, it was just a couple of reasons. One, our program and our funder were particularly interested in Southeast Asia, so we did a whole series of studies looking at that with floating solar as one component. But also that's where we're seeing a lot of interest globally, but in Southeast Asia in particular, with constraints on land, lots of water bodies, lots of existing hydropower. So in the Mekong River Delta, for instance, lots of existing hydropower plants, and So they're looking for ways to increase their renewables, but not build more hydropower, not further use that Mekong River resource. So floating solar on hydropower is something that they're quite interested in.
Okay, so we'll leave the live questions there, but if Pratik, you'd be kind enough to stick around and type some answers, because there is lots of questions still live in the Q&A. If you
yeah, I can type some up. Thanks.
Those, that's great. And we'll move on to our next speaker, which is Felix Gorintin from Innosea. So now Felix is having a little bit of a problem with his broadband earlier on, so we're going to give it a try. If it doesn't work, we'll try and do something else. So I wonder if you are there, Felix. I think we're struggling a little bit. I can see that you started doing. There's your presentation now. Can we hear Felix okay? Let's see. I'm not hearing you at the moment, Felix. Perhaps we better come back to Felix in a short while. Okay, yeah, let's come back to Felix in a short while and hope that his broadband connection is a little bit improved later on. So you are quite intermittent, Felix. So next on our list of speakers is Stefan Wiedland from the Fraunhofer ISI. So Stefan, if you'd be kind enough to go right ahead with your presentation, that'd be fantastic.
Yeah, I will. Can you hear me?
I can hear you fine. Yes, I can see your presentation now. It's in presentation mode. So
How do
you go, please?
How do I get rid of this small window here? Can you see this as well or not?
It's a little bit smaller than full screen, but we can't see any
okay.
of your notes, so that should be fine.
Okay, so I start. So thanks for having me here. Thanks for the invitation. I'm Stefan Wiedland, working at Fraunhofer ISE, and I just give you a short overview of my institute's activities. So we're part of the Fraunhofer Society, which is a big society consisting of more than 70 research institutes. My institute is called the Institute for Solar Energy Systems. It's located in Freiburg in the southwest of Germany. We're dealing with a lot of things, among them photovoltaics, which is my division. And also the photovoltaics division has a lot of things on its plate, among them photovoltaic modules and power plants, which is my area or my department in this division. And then this department, again, is divided into 3 groups. And my group is photovoltaic power plants. And we deal with performance optimization, also, and monitoring and modeling. One of our topics is what we call integrated PV, so alternative ways of installing PV, especially floating PV. And there are lots of research questions that we deal with here at the Institute, particularly the environmental impact of FPV, which is very important to German authorities because, as you may know, Germany is very, very hesitant in terms of very large PV projects because authorities are quite unsure about the ecological effects. So we try to measure those effects with existing installation, but also to predict the impact via simulations. But we also do FPV yield modeling. So we try to adapt existing yield simulations that were built for land-based sites to the FPV environment. Our portfolio is quite rich. Everything you see underlined here is dealt with in my group, and everything else is dealt with by other groups at my institutes. And there's quite a good collaboration between the involved groups. So we tackle quite a few facets of FPV on the site level, installation level, module level, and hydrological level. There are some projects that we're currently dealing with that have a focus on an FPV, one of which I'm going to present today, which is the FPV for Resilience project. And this project tries to figure out if we can actually enhance climate resilience of water bodies through FPV. So the dominant question before was, is there any harmful impact of FPV on water bodies in terms of circulation of nutrients, in terms of thermal stratification? Are any life forms affected there? But this project tries to address a slightly different question, and that's, can we quantify positive effects of FPV on, are there any positive effects, and can we quantify them, of FPV on water bodies? So the project lead is with Konstantin Ilgen, that sadly can't present today. He's a doctoral student and my office mates. And this project kicked off 1.5 years ago. And it has several ingredients. So what we want to do is we want to have different types of water bodies onshore, still water bodies, so not too many waves. We want to have actual FPV installations on them. So we approached industrial partners and we asked them if we could install monitoring equipment there. So we do there on those 3 FPV sites, we're doing monitoring, not only in terms of yield variables or electrical variables of the FPV plant, but also hydrological monitoring. So we're measuring the temperature gradients in the water just below the FPV plants, and as a reference also outside. We're measuring air temperatures, irradiance, also the classical meteorological variables. And with this data, we want to calibrate models, numerical models. Why do we want to do this? Well, at the end, we want to compute so-called Pareto fronts of electricity yield and climate resilience. We want to quantify, or we want to figure out which, given a certain lake type, which FPV design and which FPV coverage ratio gives the highest possible yields, electric yields, and the highest possible climate resilience of the lake. And this work builds on the publication that came out at the beginning of this year in Scientific Reports. And of course, you may ask yourself now, what do we actually know about the impact of FPV on lakes? What research has ESA done already? So we had a look on the effect of FPV on the layers of the thermal layers of the lake, of the water body, on the thermal stratification. And it turned out that the impact was less than we thought. So even though you have an FPV plant there, the temperature gradient below the FPV plant doesn't change. That is not too different from the temperature gradient measured at a reference point outside the FPV plant. We know, however, through numerical simulations, that if you crank up the FPV coverage ratio, so the percentage of water body surface that you cover with FPV, that there is a nonlinear relationship between the coverage ratio and the stability of stratification, of thermal stratification. But this only is relevant from above a certain FPV coverage ratio. So then there was also a sensitivity analysis of FPV-induced wind reduction. So wind reduction, the wind reduction above surface through an FPV plant is highly design dependent. It depends on the design of the FPV plants. And so it's a parameter in our calculations that changes with FPV design. And those 4 plots here show you for different FPV designs, if you will, how the FPV coverage ratio affects certain variables, hydrological variables like mean surface water temperature, variables that also could be taken to represent a water body's climate resilience. And so, as you can see, it's heavily design dependent. So this is something that we knew from previous research. And then we ask ourselves, okay, we want to systematically investigate for several lake types and for several FPV designs. Wait a second, sorry. How those FPV designs affect certain climate resilience variable that we assign to a water body. And then knowing this, how we could change those FPV designs and coverage ratios in order that we optimize for highest possible electrical yields, specific yields, and also the highest possible climate resilience of the water body. Maybe before I go further into detail, I just shall explain what exactly those Pareto fronts are. So what's a Pareto front? It's a set of Pareto optima. Sorry that I got this, I didn't. So it's a set of Pareto optima. You should just ignore the German part here, sorry. So what's the Pareto optimum then? Well, it's a situation where no action or allocation is available that improves one variable without making another one worse. Why computing Pareto fronts? Well, usually if you want to optimize a system that consists of many, many target variables, in our case, the electrical yield on the one hand and the resilience variables of the water body on the other hand, you try to set up a cost function and then you try to minimize the cost function. But in our case, the variables, the target variables are very, you can't weigh them, you can't possibly weigh them or compare them to compile a single cost function for them. So you need to work with those Pareto fronts. So this is basically the justification for why we are having a look at the Pareto fronts. And then again, what are the target variables when computing those Pareto fronts? Well, there's one set of climate resilience target variables like nutrient concentration, stability of thermostratification, concentration of oxygen, evaporation rate, algae concentration. And then on the other hand, there's the specific yield of the FPV plant. And this is those two classes of target variables we throw together, and we want to compute the Pareto fronts thereof. So what's the strategy in the project? We have a look at different FPV designs, and in order to understand how a given FPV design affects the energy balance of a lake, and with the energy balance also the concentration of nutrients and so on and so forth, we need to know about the design dependent blockage of light. So we need to know how the energy balance of a lake is affected depending on the design of the FPV plant. This we do through monitoring on 3 given sites, but also through light simulations. So this is one package, work package. The other one is taking the monitoring data that we accumulate on those 3 FPV sites, and then we calibrate our numerical models. And what are those numerical models? Well, those are a model that models the hydrological part of the system. It's called a general lake model. So it models the energy balance and the thermostratification of the lake. And on the other hand, it's a yield simulation software, an in-house yield simulation software that we call Zenit. So those 2 things are coupled. And then we browse different lake types, in our case, 3 different lake types. And then for each lake type, we go through different FPV designs and different FPV coverage ratios. So we start at 5% FPV coverage, we crank it up to 80, 90% numerically. And then we have a look at the output variables of those 2 simulation frameworks, which are the target variables that we compile our Pareto fronts with. But first of all, we generate like a point cloud of those target variables. And once we have this point cloud, we can compute the optimal surface of points that would give us the Pareto fronts for a given lake type. So just a short primer on the used general lake model. It's not our model. It was designed a couple of years ago. It's a one-dimensional model. It considers water balance equations and energy balance equations. And it has some add-ons that are also able to model biochemical processes and the concentration of phytozooplankton. And this we use together with our yield simulation software to numerically create those sets of optimal states. This, I think, as well as I can put it. And yeah. So this is basically the essence of the projects. We are starting measuring things as we speak. Numerical modeling is also underway. And the hope is that for many lake types that are relevant to Germany, we can give recommendations of which FPV design to use based on the computation of those Pareto fronts. So we would just say, okay, you need like a specific, you want to have a specific coverage ratio due to economic constraints or your business model. And with this coverage ratio, we can tell you that this design satisfies the environmental boundary conditions. This gives you the highest climate resilience possible. So this would be the aim, like recommendations of different FPV designs and coverage ratios for different lake types. Here you have a short overview over the 3 sites that we are doing monitoring at as we speak. They're different in altitude, in used FPV design, different modules as well, so that we have a very heterogeneous amount of heterogeneous input data that we can work with in order to have a good idea of the FPV design dependency of our results. So I think that's it. I have no idea if I'm already over time or not. I hope I got the main message across. If not, please pose your questions and I will be happy to answer them. Yeah.
That's great. Thank you so much for that, Stefan. That's great. So if anybody wants to put a question for Stefan, type it into the Q&A now and we'll deal with it. One came in while you were speaking, but I don't think it's particularly aimed at you. And somebody's asking, there's a Restunang was asking what type of DC inverter and capacity used on a floating PV. I think that's a more general question, not to do with your work. But if anybody in the panel wants to deal with that, has got the capacity, then have a look. I just wondered whether, because we're probably a predominantly UK audience and certainly a predominantly UK panel. In Germany, what's the progress of FPV? Is it something that is becoming? Is it happening to a greater extent than perhaps it was 5 years ago?
Yeah. So there has been a reform of the relevant laws and regulations. Up until a few years ago, it wasn't profitable to construct FPV plants bigger than 750 kilowatt peak. But now it becomes profitable, and now there are new FPV sites, plants popping up, particularly in the east of Germany, there is a construction underway of a 20 megawatt peak FPV plant. Yeah, so we are now going into the megawatt peak range, which wasn't obvious just a couple of years ago, which wasn't to be expected. So yeah, there's slow progress, but there is progress, yeah, on this front.
That's very exciting to hear. And Mike's got his hand up again. Thank you, Mike. So if you want to put your question.
Stefan, thanks again for a great talk. I noticed in one of your images you had a site in a mountainous area, and I was just wondering if there are any concerns about ice formation or extreme bad weather in the winter, and whether this would impose restrictions on the type of pontoon you could use.
Yeah, I think I don't know about the specifics of this FPV plant. I know that we have been in contact with them, and Konstantin, my colleague, has been asking this kind of questions, but unfortunately he is not available today. So I'm sorry, I can't answer your question. But of course, ice is an issue there.
Yeah. See, Stefan, if you want, I can share some details. This is Felix from UNOC. So this is actually a plant in Switzerland, in the mountains. And yeah, there's a challenge because the lake can be frozen at times, sometimes during the year. So yeah, this is one of the challenge for the float, but also for the moorings.
That's great. Well, we've got one more question in the Q&A just from an anonymous attendee, and I suppose it's just of a similar theme. What design would you recommend for the Philippines? Well, that would be rather less cold, I would imagine, but I guess it all depends on the size of the water body. But perhaps if you could expand on that, Stefan.
Are we talking about offshore in the Philippines or onshore? Because we are focusing on onshore entirely, because we wouldn't know from the top of our heads how to define the set of climate resilience variables for offshore water bodies. Because I mean, those variables, I imagine, would be very different.
Yeah,
we haven't thought about this.
It's all very particular, isn't it? There's one more from Salvita Verbra. What's the occurrence of RISO faults?
RISO. What is this? What's the acronym for?
Yeah, perhaps that's one to look at offline. So if we conclude the questions there, and thank you so much for your talk, Stefan. If you stick around, that would be great. And now I was very glad to see Felix pop up with a contribution there. So it looks like he's moved on to a different location with much better broadband. So Felix, can we see if your presentation works this time? I can see it. That's fantastic. I can see you. I can hear you. That's brilliant. Please go ahead, Felix. Thank you.
Very good. Thanks. Okay. Hello. So good afternoon or good morning, everyone. So my name is Felix. I've been involved in the floating PV business since 2017, and I will bring a bit of let's say an engineering consultancy view on floating PV with our, let's say, field experience as designers, notably on mooring and anchoring, and overall also from R&D project that we've been leading, notably in the Trust PV project. So first, just a couple of words on who we are. So we are coming from the offshore world. That's why anchoring and mooring is, let's say, our bread and butter. And we're coming from offshore wind, fixed and floating. And I've been involved in floating PV since 2017. So let me see, the slides are passing by. So I will get into quite a lot of details on FPV mooring and anchoring. But since everyone is not an expert, I will try to stay, let's say, at the accessible level for everyone. So about our experience, so we've done around 100 floating PV projects for now. Half of them have been on, let's say, dam or irrigation reservoirs, which are actually the biggest project also located there. A third, let's say, has been on cryo lakes, and let's say 1/6 has been, let's say, offshore, or in salty waters. So this is also a bit how the market looks as well in terms of split. And of course, there's we've involved all our consultants. The most, let's say, singular project I've been working on is probably the one in Afghanistan, close to Kabul, but many projects in Brazil and notably in Southeast Asia, of course. And of course, I've seen question on that. The floater technology is something crucial. It's something new in comparison to the ground-mounted PV, and is also has a strong impact on the rest of the plant design. So the size of the islands, but also the loads that you're going to have and the numbers of moorings that you're going to have eventually. So eventually on the cost as well. So yeah, just a slide. So we're working, the idea is to highlight here also how a project is developing and how you push it until the commissioning. And the new challenges that are associated to PV can be illustrated there as well. So of course, the location can be challenging. This is a project in south of France that's commissioned 2 years ago. And which is one big island of 15 megawatt. So this is challenging itself. Of course, the data energy yield is slightly different, but not so specific. The floater is going to be a major challenge, and this is a test bed located in Singapore, but there are quite a couple of them, let's say a handful of them already online in the world, and more ongoing, notably for offshore technologies as well. And what I wanted to highlight here the challenge with regard to assembly installation. So it's more serial production to assemble floats than to assemble ground-mounted PV. So it's very different. And as a last word, let's say for the introduction, the O&M and the OPEX in particular is something that is not very well known for now. The focus for now is CapEx and try to follow the downward trend, let's say, of ground-mounted PV. But OPEX is going to come at the forefront with more and more O&M tickets that are coming up, and that we are currently also looking at carefully. We're doing research on that. Maybe to give a brief recap for the newcomers in the industry. So floating PV has been on since 2007, but the real first 10 megawatt have been installed more recently, so starting 2016. So it's been only 7 years that big project have been online. Yeah, for now, most of the projects in terms of numbers have been smaller than 5 megawatt. But the biggest projects, like more than 15 megawatt peak, represent actually the biggest share of the project that have been commissioned. So I talked already about the split, but let's say dam, lakes, and is taking, let's say, the lion's share. And we're going to see, let's say, nearshore and offshore project coming on in the years to come with strong targets, notably from the Netherlands. So looking at the mooring design and what are the key criteria to actually design a floating PV farm. So you need to take into account different aspects, notably the loads that will be coming up. So I will talk about that in more details later, but of course you have the wind, the waves, and the current loads. And for the mooring design, you need to take all those conditions and to try at early stage of your project, at the feasibility stage, where you have less money, of course, to identify if, so how much PV, how much megawatts you can put on one specific project. So you'll need to take into account, in particular, let's say the load conditions. So so the extreme winds and the floods and possibly the waves induced by wind are the key aspects. But other aspects also impacting a lot, let's say the mooring design. I'll take just an example, maybe with Dam Lake, and I will go through a case study at the end of the presentation to make it a bit more, let's say, explicit. But the water level variation and the soil condition will be key, notably, and this is an example from a project we've commissioned recently in Indonesia, more than 100 megawatt peak. The challenge was the slope, the steep slope that are in the lakes to actually deploy the anchors. So going back to the hydrostatic and aerostatic loads, of course, you need to take into account, so we can model very simply floating solar PV like that with wind, wave, and current loads. And in the first instance, and in most projects for now, only static loading has been considered, and this is thanks to an analytical approach. And since 2020 and the first DNV JIP, let's say standards are coming, let's say online, but are not, let's say, everything is not aligned to actually enable engineering company as such as we are to actually perform in a standard approach the design of the moorings for floating PV farms. So, and I will detail why, of course, for offshore players that's singular, but I will explain the challenges. So in terms of wind, for now, we don't, for instance, we don't consider the turbulence. So only static loads are considered, and in order to assess how the impact of the first, let's say, rows of panels on the wind, and then its impact on the wind loads for the later for the others rows. We can take advantage of ground-mounted PV panels alignment. This enables us to get a good vision of and that's something that has been, let's say, proven also in the wind tunnel experience. You can actually derive what is the impact of wind on the first, the second, and the row number n. So what we see there is that the first few rows face a stronger wind, and that later on up to the edge you have more stable rows. This is also something that is challenging for newcomers floater technologies, because sometimes they haven't tested that. So when you ask them for this kind of data, they kind of struggle, and this can delay also your project. With regard to waves, again, we only take, let's say, static loads, or on most of the project only. So static loads are being considered. So usually the Mario formula is also used to actually derive what kind of wave you see on lakes. For bigger projects, you can work on wave propagation studies, and I will touch a bit on that. This has been crucial for a big project in Southeast Asia for us as well, in Laos. And for about current, what is considered for now is mostly, let's say, the extreme loads with regard to the flood, or let's say a dam. For instance, on the project on the Cry Lake, we have we need to consider as a risk that the dam upfront can break, and there's a regulatory challenge with regard to that, because every region and every country doesn't consider the same kind of risk in terms of a return period. So there's a strong need for, let's say, dedicated floater-specific experimental testing and site measurements, and to share a database common, so probably through standard. So of course there's an ongoing activity from DNV through GIP on that aspect. Going through the hydrodynamic modeling, so the challenge in comparison to what's happening offshore is that instead of having, let's say, one big platform, let's say an oil and gas platform or a floating wind system, or even a boat, is that in our case, we're looking at very high quantities of floating element. So we don't have, let's say, one big float, but a large amount of floats and a large amount of mooring lines. And on top of that, there's a very low draft, so very low wetted, let's say, surface. So this makes it a very challenge a very strong challenge for, let's say, a comprehensive numerical modeling. So we need to find alternatives to actually identify that. And this modeling, of course, a strong impact on the number of mooring lines that you're going to have. The fatigue is also an issue with regard to the fair leads, so the mooring connection points. And there are two other aspects. One aspect is the flow structure in itself. You've seen, because of the CapEx, that the focus has been on plastics floats. But the challenge with that is that most of the plastics floats are trying to be as light as possible, and they cannot withstand, let's say, a very large admissible load. Like typically 1 ton is usually the close to the maximum. And on top of that, there's also a third challenge with regard to the production. So the mismatch potentially with regard to the panels. So this brings us to two different approach. Either we keep on focusing on very large amount of small elements, but the challenge is that we need to find if those systems are considered large with regard to the waves or small with regard to the waves. So this will have two different approach, let's say, theoretically speaking. I won't get into too much detail there, but usually you use softwares, professional softwares such as OrcaFlex to model that. And the other approach will be to consider the full island as one object, which is flexible. And then you will need to get into account all the initial effects. So this is something that can be done and that we have already done, but which is challenging, and we need to have a more standard approach for those kind of modelings. Again, we can go into more details later on. With regard to wave damping, so this is a strong challenge on dams. As I've mentioned, sometimes you have very large, let's say, surface and fetch, so distance on which wave can build up in case of storms on dams. And this can, so of course, when we are on small lakes, this is only a couple of centimeters to, let's say, half a meters. But on larger dam with a couple of kilometers of fetch, you can actually end up with 1 meter, 2 meter HS of waves, and this could be very damaging for your system. So it's very it's a designing factor for your system. So there are, let's say, those dynamics can be broken thanks to floating wave breaker. But on that end as well, there is a strong, so it's more an empirical approach that we are taking now, rather than a very strong knowledge on how those wave breakers impact and protect eventually the floating island from the waves. So specific damping solution could be adapted to FPV industry for that. Moving on, in order to, let's say, not only for theoretical approach, but also empirically, alternative design have been chosen. So usually for, let's say, plastic floats and an individual floater, we're gonna have, let's say, per megawatt around 30 mooring lines per megawatt. So this is quite significant. And of course, at the end of each mooring line, we have an anchor. So there are different, let's say, developments we get to that. Some are looking at the mutualization of different lines, so mooring lines on one specific anchor. So this is something that we already see offshore, and that's been investigating also in the offshore wind, floating offshore wind project. We can see also some of these aquaculture approach with two levels actually of moorings. First mooring that will be very close to the island in the middle is very similar to an aquaculture farm for those who are, let's say, used to that. And we're gonna have a second grid of mooring lines. This will able to actually take out the extreme loads. And this will also enable more damping within the for the dynamics of the system. And maybe one last example, which is mostly pushed by Zimmermann in their technology, so developed with BayWa, which is very stiff. They try to have a larger fair lead capacity, typically instead of having 1 ton, moving to 10 tons or 50 tons to reduce the number of mooring lines. So now that I've been, let's say, talking about that, maybe we'll get with more, let's say, hands-on experience on the case study in Brazil. So this is an example. We are, let's say, on the large dams in the Nordeste. There's a very large lake with on which there is a dam called the Sobradinho Dam, so featuring a 1,000 megawatt hydroelectric plant. And their interest was to investigate how they could take advantage of those big lakes to actually develop floating PV and potentially develop hybrid system on those. But the challenge there, so there was already a 1 megawatt a project there, and they wanted to extend it, adding, let's say, another megawatt basically to it. And the challenge here was with regard to the data, so what we call the design basis and the data availability. Initially there was little data available, and we made it possible to enable, let's say, this project thanks to because we were able to find, let's say, those wind data elsewhere, notably thanks to the wind farm that were close by, and thanks to another thanks to an airport that was close by as well. So we had the opportunity to, and we need to do that when we lack data, to actually take together and merge different sources of wind data to reduce the uncertainties and enable, let's say, a more, let's say, less conservatism in the design. So this is very crucial at the very beginning. And I see you, Christopher, so I'm gonna close my speech. Thanks for that. Just a word about the fetch and propagation study. Same challenge. You need to understand from which direction the wind is coming. And I think critical, let's say, very good data on that is crucial. And maybe just to finish, so since we've been asking for, let's say, those database, we have been implementing two instrumentation and measurement sensors on 2 projects from this TrustPV project, so moving on rapidly. So there are 2 projects in France, one 3 megawatt in Western France, and another one in southwestern France, which is a 5 megawatt, to actually measure how the floating island is behaving in this or that kind of wind. And we will be sharing, let's say, the results of those experiments in a couple of months. I'll be very happy on that. And for those who want to discuss a bit about that, I've issued, let's say, a couple of months ago, guidelines for, let's say, design, procurement, O&M friendly concept for floating PV, based on the workshop that have been held with IPP that have been operating floating solar farms since a couple of years now. So you can find these reports on the TrustPV website. And I think I can give you back the mic. Thanks, Christopher, and thanks. I welcome any question you might have.
Thank you so much for that, Felix. Somebody's asked about will the slides be available afterwards? Well, we are recording the webinar, and I will be putting a link to the recording on the SuperSolar website in a few days after this event. So if anybody wants to check back for those, and the speakers, if they want to send me their slides and give me permission to put them on there, I'll host them as well. But certainly the recording is going to be available. Now we've got a question from Chris Binney there, and he's asking, for tidal plants, how do you usually deal with the salt deposits? Perhaps you've got some insight on that for us, Felix.
Yeah, so tidal plants, I will imagine that we're talking about plants that are in, let's say, the tidal area. So salt deposit can be a very strong challenge, of course. I will take an example of a project that I've been working on corrosion aspects. it's in Taiwan. It's used to be a 180 megawatt project, 180, so very big project. And that lake, so it wasn't a lake, but was let's say a tidal port, so port in tidal area. The salt deposit is a very strong challenge, but sometimes you don't have only that. You can have also heavy metal pollution, and let's say very let's say an extreme corrosion that could happen. So there are two aspects to your question. The first aspect will be probably to the energy yield. That's one topic, and you need to clean regularly, but that the impact of the salt in itself shouldn't be, let's say, that big. But the other challenge on the corrosion is crucial, and you need to have probes, you need to have proper design and materials specific for that location. So potentially in your development, you need to put probes as early as possible to better understand the corrosion mechanism and also their, let's say, their speed, so to say. But this is crucial, and this will be an ever more challenging topic offshore with less accessibility. And on top of that, in tropical areas, it's going to be even more challenging.
Indeed, yes. I see Mike's got a question there. Would you like to put your question, Mike?
Yeah, first of all, Felix, congratulations on taking a commercial approach to this really challenging way of introducing solar. I was just wondering, given all the challenges, do you have to modify the warranty that you offer to your clients?
What do you mean in terms of warranty? So we have a design warranty, of course, if so our clients can sue us if the design is not proper. What do you have in mind?
I guess for ground mounted now, the warranties are 25 to 30 years. Will your suppliers of modules stand behind that with floating solar, or do you have to modify that to be realistic about some of the challenges?
Yeah. So most of the biggest floater suppliers are now complying to those let's say targets of 25 years of warranty. But most of the time they are trying to make it shorter, closer to 10 years, and they add, and this is, let's say, the game, so to say, a lot of clause to that. Let's say if, for instance, the island is grounding, then you lose the warranty. If you have this or that event, you might lose the warranty, and they are designing, let's say, a design envelope. And if, let's say, the environment, so you design for a certain level of storms, for instance, of extreme winds, and if the wind speed that are recorded on site goes over that threshold, that limit, then the system is no longer warranted. This is something that happened already with a typhoon in Japan, for instance, in 2019. There was, let's say, a long settlement for this plant that has been rebuilt afterwards with more conservatism in the design.
Oh, you're muted, Mike.
It's a great answer, Felix. Thank you very much.
Okay, well, it's in the interest of time, we better move on. But I can see 3 or 4 more questions for you in the Q&A, Felix. So if you'd be good enough to respond to those, then that would be fantastic. But thank you very much for your talk today. And if you could stop sharing your screen, that would be great. And then we'll have our next speaker, who is Sophia Rocha from Lancaster University. Hi, Sophia.
Yes, hello. Let me share my screen. Yes. Can you see it?
I can see it's not in presentation mode yet, but
now
I can get it there. Yes, it is. That's perfect. Okay. Sophia, away you go. Thank you very much.
Okay, perfect. Thank you. Hi everyone, my name is Sofia Rocha. I'm a PhD researcher here in Lancaster University, and today I'm going to present you the first step of our research, which was a literature review about the physical, chemical, and biological impacts of photovoltaics on aquatic systems. Basically, what do we know about them? So my presentation is going to start with some of the motivation for our study in FPV context, followed by the purpose of our review, basically our aims. Then I'm going to dig into the results. What do we know about the environmental aspects of FPV and what is out there in the world, the research that has been done, where they have been done, what are they saying, and everything. And then I'm going to make a summary with the key findings of our search. So now, in the context of climate change that we all know, we need to switch from fossil fuel-based to renewable energy, which is the energy transition process. And this is where the floating solar panels are emerged. But are they an opportunity or a threat to the hosting system, or most likely both of them? It's an opportunity and a threat at the same time. Also, what is the current knowledge about this? What are the researchers saying about this? So we need to understand these complexities in order to assess the risk involved in deploying these systems in large scale. So now, the purpose of our literature review was to systematically report the current evidence on the impacts of FPV on freshwater systems, and then establish the types of ecological impacts that these studies of FPV most frequently focus on, in addition to the direction and magnitude of those effects. So in summary, we want to map what is out there in the world and understand how big those impacts are and whether good, bad, or even both to the hosting system. Now just a brief explanation on our methods. So I said that we did a systematic review, and that consists of first defining a research question. In our case, what is the current evidence on the impacts of floating solar panels on freshwater systems? And here, when we talk about impacts, we mean the physical, chemical, and biological aspects of the lake. So then, with that, we can translate, if I can say like that, this research question into some keywords and run into a database. In our case, we chose Scopus and Web of Science. Then we had 9,000 titles from this search. Then we scan every single one of these 9,000 and keep the relevant ones, which were about 350 papers. That we will then read the abstract and again keep the relevant ones. In our case, 58. So then we can read the full text of each of those 58 papers and do what we call a snowball search, which is basically you find a reference that was not in on your original list, you add it to them, and then you can have everything that was available at the time of the search, which in our case was, we ran the search in November last year. We were then left with 68 papers. So we read all of them and made a database, which was basically a big Excel sheet with every line containing different evidence from those 68 papers. So then we can go back to this sheet and compare the data among all the papers and all the locations, everything. So now this is our first graph. Remember that this is all related to publications that are out there. So this is not related to how many floating solar exist in the world. This is just research. And you can see that the first one goes back to the first paper that mentioned FPV and their impacts on the lake, goes back to 2014. This was a case study on an irrigation pond. And then we can see that after 2019, we had a steep rise in the publications, followed by maybe pandemic effect on 2022, with less publications being out there. And here you can see how these publications are distributed around the globe. We can see that it goes up to 5 here, the count of publications, which is still a low number. We need more research on this. And we see also that both Asia and the Americas stand out, which is a fact of both research capacity of those countries, but as well where the FPVs are being deployed. And now moving on, this is the main figure of our research. And as you can see, we divided the FPV impacts into 3 big aspects: the chemical, physical, and biological elements of the lake. And here on your left, you have a decrease on each of those elements after the FPV deployment, and on your right, you have an increase on those numbers. The gray bar indicates an empirical study, and the black one indicates a modeling study. So now, another important feature that I would like to mention is that we have more pieces of evidence, as we say, than we have number of publications. Because if I have a modeling study that makes multiple scenarios, then this will count as different evidence. So this is why here I have almost 100 evidence, but I only have 68 papers. And now you can see that the physical impacts are most frequently accounted for, and this is mainly because the floating structure is a physical barrier for the incoming radiation from the lake. So the first aspect that we can think of is the evaporation, because there is less heat coming from the atmosphere. We will have less evaporation, we will save water, and this is particularly important when we go for water scarce regions. So this is considered as an opportunity for the hosting system, and 100% of the studies reported a decrease in evaporation after the FPV deployment. And this is particularly interesting when we couple the FPV with hydropower reservoirs, because you save water from the presence of the panel, so then you have more water available to generate energy on the turbines of these plants. And now, when we talk about water temperature, most of the studies report a decrease on the water temperature after the FPV, which is also easy to understand, right? Because we have less heat from the atmosphere reaching the water. But it's important to say that this is site dependent and also highly dependent on the design of the plant. So if you have, for example, an insulated design, you can have a confined layer of air underneath between the panels and the water, and this may have a different effect on the water. And this was reported by one study that said that the water temperature actually went higher after the FPV. And here, this is also seen as an opportunity, because with climate change, air temperature is expected to go higher, and the water temperature with the FPV is expected to decrease. So then we might be able to offset this situation. And moving on to the chemical aspects of a lake, here the studies mentioned many different elements, but I'm going to comment the most frequently cited, which were basically phosphorus, nitrogen, and dissolved oxygen. Talking about the nutrients, basically phosphorus and nitrogen, you can see that is not consistent. Some studies report an increase on the concentration after the FPV, some report a decrease, the same with nitrogen, and this actually reflects the complexity of the water quality of a lake. So this is hard to simulate, this is hard to model, and this is reflected by most of the studies being empirically based. And this indicates that we need further understanding on those aspects. On the other hand, when we looked at the dissolved oxygen, it is frequently mentioned as decreased after the FPV deployment. And this is also easy to understand. If you think about the floating structure as a sheltering, it shelters the wind from the atmosphere to induce the mixing on the lake. So you will have less oxygen being integrated in the water column. And on top of that, you have less light availability for the water. And then you have less photosynthesis, which will decrease the amount of oxygen being integrated in the water column as well. And now moving on to the biological impacts, when we see what the studies say, they also, just like the evaporation, 100% of the studies mentioned a decrease in plankton concentrations after the FPV. And this is because, as I said, the floating structure is a physical barrier for the incoming light. So then you will have less photosynthesis and therefore less algal blooms, which are seen as harmful for the water quality of those lakes. But an interesting thing that was mentioned in one of the studies is that even though you have less plankton concentration, you may have what they call a shift on the species dominance, because some phytoplankton are light adapted while others are shade adapted. So, okay, you have less overall quantity, but you may have a shift in the dominance that can cascade to higher trophic levels, because the phytoplankton is food for zooplankton, which is food for fish. So then if you change the baseline, if we say it, it will have effects on higher trophic levels on the lake. So we need further understanding on that. There is not enough evidence, as you can see. And another aspect, coming back to the water temperature that I forgot to mention, is that the studies say that for higher temperatures, we have larger impacts, because when you are in warmer water, you have higher density gradients for the same temperature difference than you are in a colder lake. So if you decrease the temperature by 1 degree, let's say, in a warmer lake, this will have a different effect when compared to a colder lake. So this indicates that the impacts of FPV will be site-dependent. It will depend on where you are in the world, on the latitude, on the climate region, and also on the seasonality. So let's say we are in a temperate lake. In summer, those impacts will be different than those in winter. So as you can see, all of this is very complex and needs further understanding. Now, to summarize what I just said, some of our key findings was, first, there is not much evidence yet, but it is growing really fast. The physical impacts are more commonly investigated because of the more straightforward understanding, if you can say like that. Also, the FPV deployment improves water savings from the evaporation, and this is particularly interesting when we go to water-scarce regions. Also, the FPV was noted to decrease the water temperature, the plankton concentration, and the dissolved oxygen in the water. And finally, we had a lot of uncertainty regarding the chemical aspects of the lake. So we need more research, we need more case studies, let's say, around the globe, not only in temperate regions, but also in tropical regions. We need to interact between those results to have a further understanding of the real impacts of those systems on the lakes. That's it. Thank you for your attention, and let me know if you have any questions.
Thank you so much, Sophia. That's marvelous. Yes, ask people to put questions in the Q&A if you could. That would be great. Now, I can see that a lot of the evidence is marginal at best, isn't it? And you need to build case studies. with the Alona Armstrong's research group up there in Lancaster, have you got any past experience of case studies that you're able to conduct yourself, or have you got any that's might be in the pipeline?
Yes. We will conduct a case study in a lake located in South France. So hopefully we'll have further understanding. We'll do some hydrodynamic modeling and see the outcomes.
But I'm sure you'd be interested in any other potential sites that people might be able to
Of
offer
course.
the research
Yeah.
group. So if there's people out there that would be interested, I'm sure they'd be able to contact you or Alona. That would be fantastic.
Yes, that'd be great.
So have we got any questions? So we've got a question from Pietro Altamont. Hi, Pietro. So he asks, when the temperature decreases, the plankton concentration decreases. So why should there be less oxygen subsequently?
Yeah, so it's a complex system, because at the same time we have less oxygen being integrated in the water column from the atmosphere. So we need to how can I say it? It's complex. Like on one hand, like you said, less plankton means less oxygen consumption. But on the other hand, you have less photosynthesis, so less oxygen available, and also less oxygen from the atmosphere. So it's not as black and white as we would like it to be.
Yes, indeed. A lot of the evidence that you were illustrating there seems to be marginal at best, doesn't it? Would you say that you could say that the impact of FPV is likely to be less than the variation of water quality that you would normally find in a reservoir over a period of time, for example? You know, what kind of baseline is there available, and is there one?
I don't know. I mean, it varies. Most of the papers, they say that it will be positive and it would be good for the lake. But when we think about it, it will be good for the human use of that lake. So it's complex.
Yes, and of course you've got to think about the full ecosystem there.
Yes, of course.
Oh, I just looked to see. I don't think there's any more questions in the Q&A, so I'll just thank you very much again, Sophia, and we'll move on to our next speaker, who is Luofeng Huang from Cranfield University. So if you're there, Luofeng, and you can share your screen with us, that would be fantastic. There we are. I can see that. That's in presentation mode now. So if you want to go right on ahead, Luofeng, that would be fantastic. Thank you.
Thanks, Chris, and good afternoon, everybody. My name is Luofeng from Cranfield University, and I work here as an academic. So today my presentation will focus on the floating PV more on the ocean side. So I noticed previous presenters mainly focused on the maybe inland and inland lakes and maybe other nature resortories. But it may be hard to imagine how we would put the floating solar power plant on the ocean. So today I will present my vision of how this will basically be picture-like, and how this could be feasible based on the ongoing project at Cranfield University. So still with some a little bit background of the renewable energy, as we can see that everybody knows we are transforming our traditional energy into renewable energy, which is pollutionless. This is to reduce the greenhouse gas from burning fossil fuel. So we can see that although some countries are doing fantastic job by already producing a lot of electricity by renewable energy resources, there's still a lot of countries in the world use very late renewables. So there's still a long way to go in order to realize our net zero goal and fight climate change. So when we are talking about what kind of renewable systems we are going to use from the engineering perspective of view, one of the most important factor probably is the money. So the cost of renewable energy systems, as shown in this figure, has changed a lot over the past years, and in particular, you can see the red line that the price of PV is dropping at the quickest among others, and it has become the cheapest mainstream renewable energy on the market since 2021. Apart from that, we can see that solar PV offered a lot of flexibility compared to wind turbine or concentration solar power. This is because those renewable energy structure required big engineering work and has a large impact on the environment and required a lot of lands to build them. But for PV, you can simply even add just a few PV panels on top of your rooftop. You can also add thousands panel together to build a large power plant. So the size is completely flexible and it's very easy to install. And as you can see that if you go on the street, there will already be a lot of solar PVs on the street, on the rooftop. Yeah. So due to the its cost and flexibility, when we are doing prediction to the future, this figure shows the what IEA thinks, and the prediction until 2050 shows that solar PV will be by far the #1 energy choice, among others. And this is not so surprising compared to the with under consideration of the cost as well as flexibility. But if we look at here in 2023 now, where the floating solar PV is not there yet, and we still have a lot of other energy systems which is used as common as PV. So in order to achieve the goal in 2050, we will have around 14,000 gigawatts of PV to install. So this gives us a big question. Where are we going to install this over 14,000 solar PV panels for our world? So to for this PV technology is very special. Its energy output is proportional to its surface coverage. It's not like wind turbine. It's a lot of energy is concentrated to one point. For solar PV, it's like literally, if you want to get more energy, you have to install more panel, and which is cover more surface area. When we are talking about 14,000 gigawatts, this is corresponding to 210,000 kilo square meter, which is larger than the whole England. So find such unoccupied land is truly a challenge. As we have cities, we have forests, we have got our agricultures. Surely we cannot just remove all of these existing structures and then put PV instead. We could do lake, but as people are aware that there will be a lot of people who will be against this, because when you are going to imagine you go say that a weekend trip with your families and go to a lake that you only go, and one day you find it's covered by solar panel, it wouldn't be that beautiful. And meanwhile, we don't have that many lake space available. I think it's not in the UK. So those are not the best option. And if we look at our world map, we do have some empty spaces, which could be the deserts or the polar regions. And those areas for solar PV project is also not suitable. The reason is because of the the dust in the deserts and the snow in the polar region will cover the solar PV and it cannot work. So where are we going to put such amount of solar PV? If we have another look at the world map, you will find so much space, which is the ocean. And we know that the Earth has over 70% of the surface is covered by ocean, and it's always uninhabited, empty and flat space without human structures. So why we don't just do it on the ocean then? It appears that the future developed PV will certainly rely on the ocean. The reason is due to difficulty to find so much of the space otherwise. And if we put a 210,000 square meter space compared to our ocean available space, it will be only less than 0.1% of ocean space. So in other words, we wouldn't even feel it exists to be stored on the ocean, but it will be able to provide the energy required for the whole human being. So this is certainly promising, but it also comes with some challenges. And this is a common floating PV design. This is like a lake project. So due to the presentation of previous speakers, I will not give too much detail here. But when you make it to the ocean surface, one of the most obvious questions is how we are going to handle the waves, because the wave there will be a lot of waves in the ocean, and this will add a large load on our solar panels, and which is very vulnerable among some other effects. So we have to solve the wave effect in order to make it possible to implement the solar PV project in the ocean. So this is the motivation of the project at my university. We are developing a floating solar power plant to sustain in ocean waves, which is called the Solar to Wave project. So before introducing the core idea of the project, here is some inspirations. So in this photo, we can see that there are a lot of waves in the ocean, but inside this barrier is almost a low wave, which is like calm water, and this applies floating breakwater technology, which is this is one of the variation. And when wave comes, hit this structure, the wave will be broken, and then it will not be able to travel inside the area that is protected by the floating breakwater. So what this can mean for a floating solar project, which is if we imagine to put some breakwater in front of the solar panel and then facing the incoming wave direction. Once the wave hits the breakwater, become splash waves, and will only can travel across some buffering zone, but it will eventually become negligible before it reaches solar panel. So our solar panel will be literally installed in calm water condition, but in the ocean, and it will be technology is already available. As you know, that is already a lot of floating PV project can be done on the lakes. So once we solve the wave challenging, it will be feasible for the ocean. So for the ocean installation, since our solar panel is fully flexible, it actually can apply a modular design approach. And for every solar project, we will have energy requirements, say how many watts of total energy you will require. And then we can calculate how many solar panels will be required accordingly. And this, it's kind of like build a Lego. Once you know that how many panels you will require, you can fit it with floaters, frame, and then put the floating breakwater in front. So this will be some view of what installation could look like if you see it from a plan view. And one thing I would like to highlight here is that the breakwater will only be required to be installed on the edge of the solar power plant, which means the larger the solar power plant you have, the overall cheaper cost will be, because when your solar panel become very, very big, you will still only need the breakwater on the edge, which is one dimension. So the overall cost of the additional breakwater will be balanced by the large number of solar solar panels that you will want to install. Move to the offshore. So many people will say that yes, you got, if you are near shore, you have wave coming from only one direction, but in the offshore, the wave will come from all the directions. So what you are going to do in that scenario, and we do have a solution that the breakwater can be installed 360 degree across a solar panel. So no matter where the wave comes, it can dump it in the same way. And also for the offshore, we are very interested in seeing that there are already so many offshore wind projects going on, right? Such as this. And if you have a look at the map in the Europe, you see that people already planned so many offshore space to be occupied by the wind farm. But what's interesting is you will find the wind turbine cannot be installed too close to each other, because they will disturb each other's wind flow. So standard distance could be 1 kilometer between two wind turbines. But so there will be actually a large space in the middle which is wasted, and you probably cannot use it for anything else. How about we put some solar panel here? So considering 4 10 megawatt offshore wind turbines to be installed like this, if we see the space in the middle, there is a potential to match around 65 megawatt of solar panels. If you look in this way, after every after you have initial 4 wind turbines, every 2 more wind turbines will accumulate another 65 megawatts solar PV. So essentially, we will have the potential to install 3 times of solar power among offshore wind farm. And another advantage is the solar farm can literally share the power, cables and the electric infrastructure that we will already need for the wind turbines. And meanwhile, we could even mooring solar panel on the turbines instead of mooring it only on the seabed. So I think there is a lot of potential here. And if you imagine those space that we already planned for offshore wind, we don't even need to bother to think about find another space for solar panel. So those 14,000 gigawatts will not be a problem. So finally, I would like to introduce a case study that we are currently doing in Indonesia, which is a country with the most islands, more islands than any country in the world, the longest coastline than any country of the world, and more ocean space, a lot of ocean space. So in this country, there are 273 million people, but still over 4 million people living in over 2,000 remote islands that lack access to electricity. Those islands, if you look at, if you can follow my mouse, and you will see that there's islands such as those in the middle of the ocean. It become very impractical to collect a cable from main island to the those islands, because the undersea power cable is super expensive. So for those islands, they rely on diesel generators for at the moment to provide some essential electricity for the residents, but there's still a big gap there in order to provide energy for them. So imagine if we could do floating solar farm in the coastline of some of those islands. It will be very convenient, and we will not need a power cable to connect to other islands. So so this is one of the island that we have currently construction in plan. And if you look at the island like this, it's huge, super occupied with a lot of people living there, but it's far from the main island, so low electricity, use big diesel generators, very dirty, very expensive, and people have a lot of blackouts. So but and also on land, you can see that there's barely any space you can do unmanned engineering for this particular island. So we could install solar PV to in the coastal region to replace the use of diesel generator and give them a more clean and more sustainable and green future. This is particularly linked to the generation there, that if they don't have electricity, they cannot watch TV, they don't have mobile phone, they don't have internet. It limits the potential of the kids to learn and to access say that if you want to learn something, you could even just do it on YouTube, but for them this is not possible at the moment. So with more electricity, cheaper and more affordable electricity, and they will have a better future and then be able to go to other islands and access better education. So I know it's a big reason, but I think there's certain future there. So thanks for your listening, and I would be happy to answer any questions that you may have.
Thank you very much, Luo Feng. Yeah, so I can see there's a little bit of a debate about some publications going on in the Q&A. My first question is, I know your project is in its very early days, but can you give us a sort of flavour about the breakwaters and their sort of size and performance that will be needed to, let's say, operate in 5-metre swells? Are we talking about tons of steel here, or is it something completely different?
It's not, breakwater is not like a big secret. It's actually used a lot, been widely used across the world. And so when we have say that you want to do a solar project in the ocean space, you will first of all know that the location's wave height. Based on the wave height, you can design your breakwater accordingly. So if you want to say that we can just put a wall there, which will be super expensive and maybe unnecessary. So when you have smaller waves, you can design the breakwater to be smaller. When you have big waves, you may need a breakwater to be bigger. And a lot of experiment tests, including our own experiment shows that 90% over 90% of waves can be damped by floating breakwaters. And the advantage of put breakwater on the edge of the solar farm is because the solar farm can be very big, so heavy and float by itself. The breakwater can be fit on the edge of the solar farm and to use the buoyancy of a solar farm to lift the floating breakwater, so it reduce a lot of its costs. And also as briefly mentioned in the presentation, that the breakwater will only be installed on the edge, which is one dimension, and the solar farm can be two-dimensional. So yeah, the bigger solar farm, the more favorable the breakwater will be.
What kind of wind speeds and wave heights are you looking at on your test site in Indonesia?
We have say that commonly have 1 to 2 meters.
So that's not particularly fierce, is it? That's
No.
no.
But you may not want to go too deep in the ocean, though.
The risk is quite amazing there. Okay, Mike's got his hand up, so let's come in there, Mike.
I was intrigued by the idea of combining wind turbines offshore with solar. Lots of advantages. Maintenance of the wind turbines could be combined with maintenance of the panels. I was just wondering, in the existing installations, is there a constant distance between these wind turbines? Could you have a common design for a combined wind and solar farm?
Yeah, for the wind turbines, if we are going to build bigger and bigger wind turbines. So if the wind turbine is bigger, you will need more space for it, and the distance between two wind turbines initially maybe 500-600 meters, but now it's going to 1,000 and even larger. So you are looking at around 1 square meter in between 4 wind turbines.
If that could be standardized, that means you could roll out the same design time and time again, couldn't you?
Yeah, I mean, this is and also the solar panel is completely flexible, so the size of the solar panel can just be designed according to whatever size of the space that's wind turbines have. So yeah.
Thank you.
Okay, we'll take just one more. Charlie Allen says, how do you think you'll manage to overcome displacing fishing boats? And that kind of resonates because with the wind turbines are supposedly good fishing spots, aren't they? So yeah, so how would you deal with that as another sort of social?
We have so much within these islands, and then they do rely on fishing a lot, which is basically their life. But if we look at the island, there's so much space, in the coastal region, and certainly we will find somewhere that we don't conflict with the fishing activity. Yeah.
Great. Well, thank you very much, Luo Feng. We'll leave it there and move on to our next speaker. And yeah, thank you again. And so our next speaker is Gerardo Suman from Lightsource BP. So if you like to share there, Gerardo, so I can see that absolutely perfectly. That's great. There we are. I can hear you too and see you. That's fantastic.
Okay.
So
just to make sure, thanks, Christopher. Just to make sure you can see the presentation, because
yes, I can see that fine.
Okay, cool. Now then I'm just going to continue. So yeah, thanks everyone for joining. My name is Gerhard Human, and I work for Lightsource BP in their innovation department, which is basically looking at new and future things in solar. Yeah. So outline, I'll just quickly give introduction, some background, and then talk about Lightsource BP and floating PV, high-level performance of the system that we have, and summary looking forward, and then take some questions. So as introduction, Lightsource BP is a global leader in solar development, management and operations. It was founded in 2010 and started with 6 employees, and it's now more than 1,164 and growing. And in 2003 already there is more than 2 gigawatt of development and 4,370 jobs created. In total, about 8.4 gigawatts of solar has been developed around over 309 sites, and this is the breakdown of that 8.4 gigawatts. You'll see the Americas, Europe, Middle East and Africa, and then Asia Pacific areas, and that's where Lightsource is operating. As a background, I'm just looking at just went and looked at solar, or solar PV in general. So in 2022, the cumulative installed capacity went to almost 1.2 terawatts, and with projections that it will reach 3.5 to 3.9 by 2070, and that by 2030 we're going to see a terawatt deployment annually, sometime before that even. So for floating PV, which is floating like land-based mostly, the current situation for 2019, 2 gigawatt of capacity was installed worldwide. End of August 2020, that was 2.6, and then by 21, 3.4 gigawatt, which is shown in the graph on the right top. 3.4 gigawatt almost installed by the end of 2021, and in the future, depending on what you read, is projections for project pipelines of 14 gigawatt by 2026 and 62 gigawatt by 2030. And we see the Asian markets, China, India, Indonesia, growing pretty much, expanding very fast. Then marine floating PV. So this is something that Lightsource actually got really interested in because of a lot of questions being asked. So we did a review of floating solar on offshore, and key findings that we came across that there is a small number of small marine floating PV pilots that have been deployed, and these range from 10 to even 500 kilowatt. There are several challenges that exist: the harsh environment that you sit with corrosion, humidity, mooring line failures, salt deposits, bird fouling, and then marine traffic interaction and policy, and I mean there's many more. It's a really new environment that solar industry is moving into, so everything almost has to be developed from new. Hybrid projects allow the sharing of infrastructure. Has been mentioned by the previous speaker, which is actually quite nice, that's not only export cable substations but also floaters, mooring and anchoring, supply chain, and manufacturing lines. So if you can build floating PV on the same floaters as the floating solar, or even the wind, or not the wind, floating wind, and the wave power, then that brings down costs considerably. There is, however, still major barriers, technical barriers in deploying marine floating solar. The potential is obviously, it is there. There's been studies or reports at least for offshore floating PV potential by for the Netherlands, for example, 45 to 51 gigawatt by 2050. And the potential is there to reduce the cost by sharing infrastructure with other marine technologies, land availability, and large potential in PV for island shift focus to water. So Indonesia, big example of that. And then there's huge potential of floating off solar PV in the calm tropical regions, which was in a recent global atlas for offshore floating PV, which gives numbers of over 720,000 terawatt hours in these conditions of smaller than 6-meter waves and 15 meters wind speed. And I'm not a solar floating expert by far, but it's just sort of ironic that with floating PV you want to stick away from the wind, and with floating wind we'd like to have those winds. So it's interesting what the combination is going to be there if you have the wind and PV sitting next to each other. Just give some benefits and challenges of floating PV in general. So reduce land use is a big benefit. You're not competing with agriculture and with green areas. And then installation and commissioning is given as a benefit. The installation is fairly easy, and then in decommissioning you're not, I mean, you're only removing anchors and ropes and the floater, so you didn't disturb anything which in the land-based PV would have foundations and possibly piling that you would have to remove, a lot of underground cabling. So that it could be a benefit. Reducing water evaporation, that was mentioned by Sophia, I think, and then in especially water scarce areas, that's a really good thing. Cooling and tracking, I've seen really nice tracking systems that basically uses pumps or pumps that just in a vertical axis tracking just turns the around floating structure, and that's quite a very efficient way to do tracking. Then there's also tracking systems, the horizontal axis tracking systems that work on buoyancy, and that's quite cool, and you can even combine the two. So you can have really nice tracking systems, and then there's mentions of the cooling effect, which benefits and could produce up to 16% more energy. Hybridization opportunities has been mentioned, and for land-based hydroelectric is nice because you can have the benefit of storage and increasing the capacity factor, and then environmental benefits. Some that has been mentioned, synergy with fishing, so you can combine them with fishing shrimp farms, limiting the greenhouse effect, and I think Sophia mentioned about what happens. Well, if with land-based there's radiation, a negative radiation effect, and with the just I have something interfering with my screen at the moment. Can everyone still see? Sorry, Christopher. Okay, I'm fine now. And the reduction of specific energy costs if with the increased energy, possible increased energy output. So the challenges would be corrosion, especially on sea and brackish water in land-based water bodies, which is brackish. That could be an issue. Fluidity, so PV systems are continuously moving, and you've got a lot of hinges, and that could contribute negatively towards the life of these systems with a lot of wear. Recreation could be an issue, so some reservoirs are used for recreational activities, and this could be an issue on land-based water bodies. This is can be controlled at least, but out at sea it is recreation, and then the added just normal marine transport, marine vehicles, and I've already seen at least one incident between a wind turbine and a ship, and with floating solar and the increase of energy systems, you can only think that this would increase, and then obviously you sit on water, so winds and waves is definitely a concern. So the Queen Elizabeth floating solar plant that Lightsource BP developed and currently build and operate and maintain is located at the Queen Elizabeth II reservoir basically in London, near Heathrow. Actually, it's connected directly into the Thames Water private network, and it's got a capacity of 6.3 gigawatts. It's made up of 61,000 floats and 23,046 solar panels, and has 177 anchors and covers a land of 57,000 square meters, which is basically 10% or less than 10% of the reservoir surface, and it's capable of generating around 5.8 gigawatt hours a year. And then sorry, that is a second point or additional point, secured by professional divers. It was successfully completed in March 2016, and at the time was Europe's largest floating solar plant. Okay, sorry. Here we can see in March 2016, it was the biggest. Sorry, I just need to close this door. And sorry. March 2016, it was deployed and was then second biggest in the world. And then in April 2016, 20 megawatt from Japan was installed. But yeah, it's been running ever since. And since then, the floating solar industry has expanded. And it's already been mentioned, the 320 megawatt in China. And I mean, as the numbers show, it's got a lot of potential. I couldn't do much or get a lot more information about the performance, but what I could do was compare the performance out of the Queen Elizabeth with solar plants that has been built in the area that was built around the same time using the same inverters and modules, and all of them fixed tilted. So the floating PV had about 3.5 to 10% lower yield in terms of kilowatt hour per kilowatt peak installed per year, and I mean, there's a couple of reasons, and one could be that just the tilt is completely not optimized, whereas the other farms it was, and then the floating PV had between 21 and 28% more in power density in terms of kilowatt peak per square meter which was installed, and in terms of the energy density kilowatt hours that could be harvested per square meter, it was also 12.5 to 25% higher. And as I've mentioned, the tilt's not optimal as you would have on the land-based systems, and O&M and operation and maintenance cleaning especially is actually quite difficult. So that's a big challenge that they do sit with, and there is some wear and tear issues specifically with the floating systems. In conclusion, where space is challenging, floating PV is definitely a better solution. It gives a lower kilowatt hour per kilowatt peak, but a higher kilowatt hour for the surface that's being covered. Global floating PV has taken off in the last couple of years, and especially in Asia, but also in Europe, we see a lot of attention and a lot of opportunities, projects being mentioned. And looking forward is for Lightsource BP at least, is that we are not actively busy with any floating PV, but we do see it as something that in future is very important. So we are constantly looking at new technologies, talking to developers, looking at markets, and marine floating solar has actually come up as a really interesting one. And one of the important things that comes out of our sustainability is the move away from virgin plastic. So the need for those virgin plastics, HDPE floaters is something that we'd like to move away from. And that's me. Thanks, everyone.
Thank you very much, Gerhard. That's fantastic. So yes, questions in the Q&A, please. Now, as far as I understand it, you're like a construction engineer. That's your background. And what kind of challenges do you think the working environment poses for the construction team? Getting out there on the pontoons and assembling the panels. Do you think that's going to be tough?
Well, I think it's so. I mean, it depends on what type of system or how the system is designed, but hopefully everything is essentially connected and put together on land and then or on a barge and then just dragged into place. It does require, like the anchoring and mooring systems does require specialized people and services, but it essentially isn't an issue. I think the maintenance is going to be the biggest challenge.
It certainly seems so, yes, and that require regular attention, won't they? And so I've sort of read anecdotal bits about people installing them and sort of on the pontoons and banging their knees on the corners of the panels, and that sort of issue has cropped up.
Small stuff.
When there's thousands of panels potentially going to be installed in this way across the world, it's going to be a big challenge compared to doing it on land on a robust environment.
Yeah, but what is happening is, especially on land-based systems and going to the extremely big solar plants is a move towards, I would not call it a move, but there's a need for changing the way that solar is being developed and built. So the deployment needs to be faster. The everything just needs to be faster, and I'm going to say cheaper, but that's not even the biggest issue. It's just the speed at which it's being deployed. And some of those industries and companies are looking at how they can alter their developed techniques or systems to the floating industry, because it's going to be such a massive industry where you basically park with a container and just pull everything out of the container, and it's completely factory assembled and connected. So that is the sort of the future, and that's going to make it much easier. Maintenance is still going to be, maybe you pull everything back, swap it with clean ones.
As ever, yes.
I don't know. Maintenance.
Mike's got a question there, so if you want to put your question, Mike.
So you mentioned that corrosion is going to be a problem when putting these modules close to water. I would imagine the AR coating will also suffer. When you look at the procurement of the modules for this application, do you specify any difference to the ground-mounted modules that you use routinely, or are any of the major module manufacturers looking at this application in particular?
I would not be able to tell you. I don't think there was any difference, but I wouldn't be able to tell you exactly if there's a difference between specification. I think the connections and the electrical side of the panel definitely, but on the coating, I'm also not even very experienced.
Do you think as the application grows, then some of the module manufacturers may start to specialize and look at issues like corrosion?
I think if it's especially if the coating is going to be a definite issue, then I think it would be an opportunity at least.
Yeah, thank you.
Lovely. Right. Well, I think we'll leave it there. Thank you very much, Gerhard. And we'll move on now to Majid Karimurad from Queen's University Belfast, who's, I think, is going to do some more offshore stuff. So take it away, Majid.
Yes. So, hello everyone, and good afternoon. Can you see the slides well?
Yes, I can see.
Okay, very good. So, good afternoon. This is Majid from Queen's University Belfast, and I talk about dynamics of floating solar, experimental and numerical assessment. This is mainly based on the work that has been done by my PhD students, Gautam and Dolan, and also we have industrial project. And then toward the end of the talk, I mentioned very briefly about that one. So this is me. I'm reader in marine and coastal engineering at Queen's University, and as academic, I have different roles, as you know. But then my interest is offshore renewable energy, in particular offshore wind, floating solar, wave and tidal. And in the core of it is marine structure dynamics, hydrodynamic. And if you are interested, please refer to my papers and then my books also. At the right-hand side, you see the picture of those. As mentioned by others, we are living in climate emergency. So some actions definitely is needed. Already there have been some move, but still we need to go very robust toward having this climate change finished, hopefully, and then deliver sustainable energy and then ensure that carbon is cut down enough to limit the temperature rise. And when it comes to renewable energy, global renewable energy has a very good perspective. The forecast is saying that we have by 2030 almost $1977 billion. That is the forecast. And then with the global annual growth rate around 8.4%, which is very good. This happens yearly from 21 to 30. If you look at the overall global energy, and which is depicted by International Energy Agency from years ago up to 2050, then we see that by 2050, almost 85% of energy is coming from renewable energy, and big part of it is wind and solar is mentioned by others as well. So almost 1/3 of it will be wind, 1/3 of it will be solar. And then it shows the importance that then proper research is done and then industrial development is going ahead. But why floating solar energy? Some of these mentioned by previous speakers. So it's an alternative, an attractive source of energy. This helps us with less strain land usage for densely populated areas and natural cooling effects that helps efficiency gain, increased irradiance from reflectivity of water, and then solar in conjunction with hydroelectric plants, then it can optimize energy efficiency and improve system reliability. Also, we are thinking, as mentioned by others, by co-locating with offshore wind, wave energy. You can combine this with aquaculture and also together with hydrogen. I think it will be very good from the source of producing energy up to using that energy in cities by transporting the hydrogen to our cities and then having it used by us. Very promising perspective. As mentioned again by others, it has been installed in many places. Almost everywhere they have got floating solar. A sort of it from very small units, say 20 kilowatt up to 50, 100 megawatt on board, which sounds very good to me for a person doing research in this area. But you see North America, Europe, Asia, Pacific, and then the other places they have installed it. But one of the reasons is that we have a very established technology on land, especially when it comes to sheltered waters. It has been proven. It has started many years ago, but still the portion that we have when it comes to floating solar to land-based installation, it is very tiny. But by 2050, when 80% of electricity should come from renewable energy and 1/3 of it is from PV and solar, then we hope that a very big portion of it is floating. And this is in line with the point that 40% of world's population lives within 100 kilometers of the coast. So moving toward having nearshore, offshore, then it is very rational. And then it's wise thing to do, providing energy that in places that's close to use of them. It's very obvious and it happens eventually. And floating PV can be up to 17% by 2030 with an annual growth rate of 30%. This brings a huge market, job creation, and then happy lives for our children. Examples of floating solar around the world. I'm not going to detail of them, but it shows that almost everywhere they have got it from different types. You see the variety of it in different countries, how they have been installed, using the previous technology from aquaculture, from offshore oil and gas, from wave energy, and then also having different pontoons or different platforms, tracking technologies. And Dolan did a very great job in providing a review paper that is accessible. That in the box you see it's highlighted there. So if you're interested, you can refer to that one and read more. But we have industrial need to move further, improve then this technology ahead. But what is needed the most is development of numerical codes validated against experiments and field tests. This should account with wind loading, hydroelastic responses, and then understanding very well the load and load effects. And definitely we need data from R&D projects. So that is very important to have demonstration projects that they fit to our numerical tools for enhanced and validated codes. This ends up with better designs, hopefully lowering the CapEx down, lowering the OpEx down, and then having better designs. Also, it's mentioned to then standards and code developments. There have been already some movement around that, and we have seen standards for floating solar, but new version of it should be produced based on the new knowledge developed hopefully in the new years. This should account co-design and multi-criteria assessment, accounting for the entire life cycle of the structure. Someone asked about the decommissioning. Yeah, that should be accounted for definitely. And then we have to ensure the structural integrity, reliability, sustainability, and environmental impact, as mentioned by Lancaster researcher today. So, but when it comes to investors, it's their money. So, and that one is a matter of safety, which should include reliability and cost. But what answers to that is understanding better the gaps. So we have lack of knowledge in different aspects. One of it definitely is about dynamic responses, load and load calculation, which is very important for power production. The structure is moving definitely. And then also you have the loads like bending moment, shear forces that leads to failures and fatigue. So extreme value analysis for ULS, ultimate limited states, for fatigue, serviceability, and accidental should be done. This leads to how we think at Queen's for this particular subject. We think about experimental analysis, experimental assessment, as well as numerical simulations, validating calibration of these codes, to providing better tools that they can estimate the responses well. And that helps the designers to ensure that their design is better, having fast approaches that they can explore the design space. So it's like physical testing and numerical simulations going hand in hand together. This is what we do using our Flume here at Queen's. We equipped with motion capture cameras, QALYSIS, load sensors, wave gauges, very well calibrated wave production, and then study the wave interaction with the bodies to understand how the structure reacts. Especially the structures, as mentioned, they have a small draft, so they can emerge from the body, go to the body, go to the water body, then interacting nonlinearly, having a nonlinear diffraction and radiation. Viscosity is important and damping that they are produced. and also attenuation of the wave, interaction of the array together. So these points should be assessed further to understand, because the code, some of them that they are available for industry, they are quite linear, and they are not they cannot account for some of these points. For example, instantaneous positions and then changing the hydrodynamic properties. But then we have started looking in detail different loading and load cases, different CSTs with different condition and stiffness to understand the behavior of structure when it is interacting with the wave. For example, looking specifically for overtopping in this case, which was very important, and dividing the responses to two parts when you have drift and resonances around that one, and when it is coming out of the water entry and exit, and then a slamming and also even a sloshing between the cylinders that we have, and blockage effect for sure. So it's quite interesting phenomena we have seen. And then our aim was to study it further. At the top, then you see the paper that's recently accepted in Journal of Offshore Engineering and Science by Dollond. So it's about the experiments that we have done and documented, well documented. So you might refer to that. But then having different sea states, we have started to look into detail that how the loads they are changing, how the responses, especially when it comes to mooring design, then the overall surge force is very important. So we have had a very thorough investigation that when we have the single cylinder compared to double cylinder, and then the attenuation wave and interaction of these columns, cylinders, how they are affecting those, and then how the overtopping appears in some sea states and not, and how it is different from regular cases to irregular. These small details can change a lot of things, because some of those in 1 in 100 can result in failures, fatigue, and resonances. And this should be known to designers to go through their design space to change perhaps the parameters that they are governing their design. Say, for example, the gap distance or dimension of the cylinder, or having a close look at their hydrostatic properties and the link that they have between this hydrostatic and the nonlinear dynamics appearing. So when it comes to irregular sea states, then we had a look specifically for superharmonics, and then harmonics that are appearing, not just only the linear part of the response first order, then second harmonics, and then third harmonics, and then resonances, they are appearing. This resonance, I mean, is kind of usual suspect for those people. They know they are in offshore business. They know that, I mean, it's one of the critical things. And it's a matter that then how much damping you have in the system. Perhaps some of a structure damping you can get, but they are not a lot. You cannot count on that. And then it's the matter of how much then you have hydrodynamic damping, both coming from the potential part and then viscous part. So these things then it can result then to reducing the responses, hopefully, and then changing your governing parameters to have a better design. Our next move was to have a potential flow. This is nonlinear hydrodynamics. It is mainly done by Arash, who was here as a postdoc. Now he's a lecturer in IST in Portugal. So this one is a potential flow software based on boundary element method and mixed Eulerian Lagrangian in time domain analysis, accounting for instantaneous wave body interaction. So it's quite detailed. It can capture a lot of parameters that I mentioned, and then it used the force order Runge-Kutta time domain integration. We had to study them versus the experiments that we have done for decay tests, for the linear analysis, irregular cases, and understanding of the response of the structure. And then for most of the cases, we captured very well. If you are interested, you can refer to his ocean engineering journal paper that is written there. Both for motions and responses, we have got very good agreements. And then even we were able to capture some of these nonlinear phenomena, and not all of them, because some of them will be missed because of the viscous. And that was the next move, basically, with Gautam, that he's doing rounds analysis using OpenFOAM and using K omega SST turbulence modeling, and with a thorough the detailed mesh that he has with the proper boundary conditions, accounting for the wave, both in regular and irregular cases, he had a very good performance of getting very well validated code now, both for motions and responses that we have for the overall loads. And then we are able to capture the coupling between the heave, pitch motions, and then also the interaction that it has, the structure it has with the body. Again, this has been thoroughly documented in a conference paper by him in OMAE presented last year in Germany. So definitely some of the nonlinearities we cannot capture, especially as stiffness is going high, we are not able to capture everything, but to a very large extent, we are satisfied now with the viscous numerical wave tank that we have. And then it's a matter that further we develop some of small deviations we see, but I think it is in a good order. And even for irregular cases, and then frame that the process that he has done for the Jones-Webb spectrum that has been implemented, we have got very good results as well. So some of them has been shown here. Especially, we are happy that we can capture the higher order loading and responses very well also, which is quite good. So as I said, some of these underestimations happens because of the nonlinearities. A lot of them we can capture, but further we develop. When it comes to axial forces, presence of second hormone is important, especially if you're using the linear codes. That should be a point for you to consider, especially for mooring load analysis, because they are trying to link these axial overall loads with your mooring loads, anchoring loading, and then also even for some of the motion responses, higher order can affect your design. So again, these things has been also presented in RENEF conference in Portugal. I mentioned that we have industrial project also. We have a case center for advanced sustainable energy, and they have funded us. We have a floating solar energy, a contributor to decarbonization project, which we are working with our industrial partners, Solar Marine Energy, B9 Energy, Synergy, and Brookall Estate. This is a very good example of successful project that we are doing now to have immediate application potential in Northern Ireland, in UK, and contribute to the Power to X, and then creation of jobs. We are looking for demonstration phase now, and hopefully in near future you can get more insight to the project. Ongoing stuff that we do is also wind generation that we are doing at the moment to calibrate the wind, and then interaction of the wind and wave is quite important. As someone mentioned in the chat, I've seen they were asking about the wind loading. Yeah, that is very important. We have turbulence loading, and then especially in the boundary layer, when you have the interaction of the wave and wind together with the structure, is quite challenging. This is the steps that we have now at the moment, and we are going further ahead to help industry moving forward. If you have questions, please refer to me, and then I get back to the team and I provide answers. Thank you so much.
Thank you very much, Majid. Now, I can see there's a question for you in the Q&A already. What is your opinion of submerged FPV? It will certainly get rid of the wind issue, wouldn't it?
Yeah, but how much it should be submerged, that's the question. Because if it is at the splash zone, then it's a matter that I think if you are still in that splash zone, say if you have waves of HS of 2 meter, 3 meter, 4 meter, and then you are just submerged by like a 1-2 meter, that's a big question. So we have to look at it perfectly in detail. But there is also another question, that how much then the solar and then the capacity of the solar will be affected when we have it submerged, because going through the water column, and definitely you see these very in mangroves that dies out when you are going deep. So perhaps, I mean, as far as I remember, perhaps in the couple of first meter will not be affected very much, but still I think you know, for most of them, cases, the dynamic pressure of the wave, it is quite active in the less 10 meter. So if it is more deep than, say, if it is deeper than 10 meter, where we don't have, I mean, very much hydrodynamic actions of the wave, then I worry about how much energy can penetrate.
Yeah, surely it's getting dark by that
Yeah.
point. Milad, who posed the questions, suggesting 30 to 40 centimeters.
Oh yeah, then if it is in a lake, can be quite different if you're offshore, because you have like a waves easily of a chance of, say, 3-4 meter and beyond, and then even it can be more difficult because of the slamming that you have on the flat surface. So imagine that then you have the crest and then this overtopping, and you have a flat surface, and then tolerating that load is another challenge in my view. But I'm not saying that it is not feasible. Studies are needed, in my view.
Yeah, it's interesting. We've got another question for you from SB Kim. So at the moment, how many connected units of a rigid body can you simulate in your wave structure analysis?
Right now, we just have 2 at the moment, as I said, because of the experiments that we have done. Also, they were 2, but having more, it helps definitely. And but it's a question of what you are looking. If it is joint loads you are looking, some of the other softwares might be more proper for this. What we are doing here is detailed analysis of interacting these 2 body, looking at attenuation, and also how one body is acting toward a wave. So we are looking at detailed analysis rather than very global dynamics at the moment.
Okay, and Pietro's got a point he's making. So about why don't you observe a real system? Have you had an opportunity to observe a real system?
Yeah, that one will be the installation mode as a demonstration project, hopefully.
So that's to come, hopefully. Yes.
Yeah.
That's fantastic. Well, I think that's all our questions. So I'll just thank you very
so
much, Majid. That's excellent. And we've got our last speaker, and that's Spiro Angeli from Glasgow Caledonian University. And Spiro is going to give us just a micro presentation to take up the last few minutes of the session. So take it away, please, Spiros.
Yep. Please let me know if you can see my screen okay.
I can see it, and it's in presentation mode by the
Excellent.
looks of it.
Excellent. Thank you so much, and thank you, Christopher, for hosting this event, and thanks to all the speakers. I think it's by the end, as we are approaching the end of this workshop, I think we can all agree that despite the all the progress we've made on floating solar PV the last 10-15 years, there is so much research needed to be done. So that's a good incentive to all young researchers out there looking at floating solar PV, such as myself, young, not in age, but in years of research. I need to clarify. So thanks for that. So I'm conscious that I've got only 5 minutes for my slot. I'll just start right away. So as more and more installations of floating solar PV will start coming up, I think what might be a potential issue in the future is site identification. We are seeing that with onshore wind just now, as developers struggle sometimes to find suitable areas of developing their wind farm projects. So this may be another issue FPV may face in the future as the technology keeps progressing, and we witnessed more and more FPV installations across the world, and hopefully Europe and the UK. So as a background, myself, I'm an environmental consultant working for RSK, and on a part-time basis, I'm doing my PhD researching the feasibility of floating solar PV, mostly in the Mediterranean region. However, I got the opportunity through that to look at the UK as well, mostly on a site identification analysis approach. So what I'm going to share to you with you today is just my approach towards finding suitable sites for the deployment of floating solar PV. So let's move on. For our actual analysis, initiated through a knowledge exchange program, and the actual question was, are there at all any lochs in Scotland that floating solar PV can be deployed to, regardless of all the socioeconomic effects that may be involved with? And so the site identification criteria we set initially was the proximity, the available surface of water bodies, first of all, and there has to be enough water bodies to accommodate that technology, not just fitting enough, ideally larger areas of water bodies that sections of them can accommodate that technology. And then if there's existing road infrastructure linking to the water bodies, because conscious of the terrain and topography of Scotland, there's many water bodies that are inaccessible. The proximity, of course, to existing electrical infrastructure was another thing that was considered, and and last of all, avoiding special protection in designated areas. So the data we used in this analysis was a couple of years ago. Some of that is currently expired, but we still have the results from that analysis. So one of them was the UK-wide Water Bodies 2018 database that was acquired from ArcGIS Online. And another one was which is still available, the OS Road Infrastructure database from Esri's Living Atlas. Electrical infrastructure database from ArcGIS Online again, and the World Protected Areas database from Esri's Living Atlas. Okay, what I don't mention here is the tools that we used in our analysis, and the way we developed this analysis. It was very straightforward and simple, so that it can be applied to other regions of the world as well. It doesn't have to be specific to the UK or Scotland. And it's very simple in terms of what geoprocessing tools we used and the information we were looking at the time. In terms of the geoprocessing tools we just used the three main ones, spatial analysis tools we used, and one of them was Buffer, creating buffers around already existing infrastructure, Clip for clipping the extent of those buffers to the areas of interest, and last but not least, deriving null locations, just setting our criteria in a table and getting our end results, which I'm going to share with you a bit later. So to get onto our maps, so we, as mentioned earlier, we started with a much wider database that covered the whole of the UK, and as you can see on your screen, probably is not that clear at this extent, but there's in the blue color you can see the surface of water bodies across the UK. It's not an exhaustive list, I've got to say, but it was a good baseline database to begin with. So getting that, the next step was to just limit our study area to Scotland, which is still a massive study area to be looking at. And as already mentioned, the first thing we're looking at was the proximity to road infrastructure. So when we brought that in and created buffers around it, looked like this, which may not make much sense now as you say it, but we'll take a closer look in a second. So basically what is shown on your screens is a 500 meter buffer in all directions from all road infrastructure that covers roads A, B, and motorways. So it doesn't cover minor roads, for example. So to take a closer look, it looks sort of like this. So this layer, which extends 500 meters in each way from road infrastructure, as you can see, and in some cases there's good proximity to water courses that we're looking at, and in some other just limited access, as you can see. But it's quite natural for countries that have a similar terrain, such as Scotland. So it's not a big surprise. So to take closer look. So the next step was to, let's see if that, this is a bit blurry, but hopefully you can see that. So it's a screenshot from the report. That's why it's a bit blurry, so apologies for that. What's actually shown is the actual water surface layer. And then on top of that, the buffer around the road infrastructure, which covers sections of the surfaces of water. So the next step was to clip that layer and just to have that basically what is covered in our buffers, what intersects with our buffers on top of the water surfaces area. So that was the end result, as you can see. And once clipped, you can see right here, this is what we got, the layer showing basically water bodies that are accessible via already existing road infrastructure. Okay, but we still had a massive database to work with, as this covered the whole of Scotland, and wanted to narrow that down a bit further. So the next step was introducing electrical infrastructure. So bringing in the already existing substations and power stations in Scotland. So as you can see right here, there's a buffer created around a power station and a substation, which is combined here. This is the Cruachan pumped hydro storage scheme, and another substation right here. So to narrow that down, we sort of following the same approach, clipped once again our layer, and that resulted in this. It's basically a much consolidated approach, because the existing layers just now, you can see it just covers water surfaces that are available, that are accessible by car, excuse me, and are in close proximity of electrical infrastructure. So we initially started with thousands and thousands of available water bodies when we started, and then we brought that down to more than 100 with this sort of approach. So you can see bits and pieces of available available water surfaces scattered around. But then again, we had to take a step back and see which of those areas are actually suitable for deployment. For example, because of most people are aware, Scotland has quite a lot of areas designated for their environmental importance and significance. That is always taken into consideration when you're looking at renewable energy feasibility studies and planning applications, of course. So taking a step back, I imported what you can see on your screen is the World database of protected areas. Again, it's not inclusive. It doesn't contain local designation, but it's a good indication of what should be avoided when you're looking at renewable energy developments. And as you can see, if we click on one of the features, it comprises national parks, national nature reserves, sites of special scientific interest, and national scenic areas, and quite a lot of ocean protected areas as well, and things that need to be taken into consider when you're looking at feasibility studies for floating solar PV, of course. So the next step was to omit from our data set was included in those areas. So as you can see here, Loch Lomond is one of the most promising loch for the deployment of solar PV when it comes to access and already existing infrastructure, but there's quite a lot of designations stacking up, as you can see. So just through that next step, got rid of that, and from more than 1,000 potential sites, we limited that just to over 50 sites we can take a closer look at in terms of design requirements and other attributes that will be important when you're looking at that. So just to close up, again, this sort of site identification analysis can be used in any region of the world, utilizing the same tools, the same databases when they apply. So if you've got any questions, I'll be more than happy to answer them.
Thank you very much, Spiros. I can see Pietro's made a good point in the Q&A. So you've restricted your analysis to roads. So what's the importance of that? Is it because you're thinking about, well, stuff needs to come by land rather than on ship, or is it future O&M considerations where somebody's got to come and
strictly for access. So because we've had such a big data set to begin with, we thought it would be sensible to look at areas that can be accessed by car, so not requiring to build new tracks to get access to them, and build a potential FPV array, because that would of course limit the options and make it more difficult, not just financially, but from a planning perspective as well.
That's marvelous. Well, that looks like a very interesting tool there, Spiros. Would you like to say anything about the developments in, is it Shetland, that the Scottish government have publicised recently about floating solar and their investment in it in the future? I believe you've got something to do with that.
Apologies, Christopher. I'm not aware of that, to be honest with you. So I'll need to go and have a look now that you mention it. This analysis was done a couple of years ago. So
okay, right.
Yeah.
So okay, well, I think that brings us to a close. So thank you very much, Spiros, and thank you to all our excellent speakers this afternoon, and thanks to all the attendees for coming along. The webinar is being recorded. As I say, I will put that onto the SuperSolar website in a few days. And if any of the attendees would like to send a message to the speakers, please just drop me a line and I'll forward that message on. If you can't find their contact details elsewhere, you can find my contact details on the SuperSolar website. So just to say once again, thank you very much to everyone, and goodbye. Thank you.
Thank you, and goodbye. Bye.
Thank you. Bye-bye.